Hi, I'm Kevin. Welcome to my cave. Last time we got started on learning about transistors. We heard how a BJT out of circuit behaves as two diodes, and how to determine the type of an unknown transistor and identify its leads. This time, we're going to build our first transistor circuits, current sources. This is the point when in a conventional electronics course, I'd start going on about how the voltage difference between base and emitter induces a depletion region in the base, allowing majority carriers to be injected from the collector, flowing to the emitter. And are you still awake? Hey there! You in the back row, wake up! Now I agree that physics is really important, and learning almost never goes to waste. But I'll also confess that I've never actually used that information while designing a circuit. A course will then usually go back to the analogy between the flow of electricity in wires and the flow of water in pipes, and liken the transistor to a valve. There's nothing wrong with that analogy if you find it useful. In fact, it gives us an easy way to remember one of the most important facts. A transistor acts as a variable resistor. It transfers some signal in its base to the apparent resistance between collector and emitter. That's where it gets its name. It's a transfer resistor. It doesn't add power to a circuit or make current flow. Its variable resistance allows varying amounts of current to flow. Ohm's law still works. The next thing a course will likely do is to ask you to imagine a little person inside the transistor whose whole job is to adjust the resistance to have something at the collector controlled by something at the base. And there's an equation written on the wall behind her that purports to describe what she's doing. Controlling collector current by observing base current. But I'm consciously not explaining that equation any further yet. I'll get back to it, I promise. If I know YouTube viewers, I know that the moment I do, there will be a fistfight in the comments over what's the real model of the transistor. And that's just not relevant today. Instead, I want to give Transistor Person a simpler job. Assume that the collector voltage is always above the emitter voltage by at least a few hundred millivolts. That's for a small signal transistor. It'll be higher for a power transistor. Check the data sheet for saturation voltage. Assume that all the current in the collector also passes through the emitter. That is, that the base passes no current. This is false, of course, but for a typical transistor, emitter current equals collector current to within 1% or so. Adjust the valve, the collector-emitter resistance, wherever it needs to be to keep the emitter 1 diode drop below the base. There's a whole elaborate behavior working behind the scenes, but we can do at least a few useful transistor circuits, thinking only about this rule and saying nothing about how it's accomplished. Thank you, Transistor Person. Let's look at an example of a current source. In this schematic, I've made a voltage divider to give me a voltage of about 5.6 volts to feed to the base of the transistor. It's actually a little less than that, because I use the nearest standard 5% resistor values. The rule I just stated says that the transistor emitter will show a voltage 0.6 of a volt below the base, or 5 volts. That will push a current of 5 milliamps through the resistor R3. And the collector current should be about the same 5 milliamps, however I turn the pot RV1. I've built the circuit up on the breadboard here. I have the blue meter showing the collector current and the yellow meter showing the collector voltage. With the collector pot all the way down, I see about 4.5 milliamps of collector current. As I ramp up the resistance, the collector current stays about the same. There are some tiny variations. In a later episode, I'll discuss a phenomenon called the Early effect, which is what causes these variations. But as the pot comes closer to mid-range, the current starts to fall off. If we look at the collector voltage, what we see is that the resistor is now so high that the voltage drop across it has the collector down to 4 volts. The transistor is a valve, not a pump. It can't pull its output significantly lower, so it can't provide any more current. It's transitioning to a state called saturation. At that point, the collector to emitter path looks like a small resistor, and our current source becomes little different from a voltage divider. Let me measure a few voltages and currents so that I can graph them. I've graphed my numbers in a spreadsheet, and you can see the behavior. When the transistor is in the active region, it's regulating the current pretty tightly, around 4.5 milliamps. When it goes into saturation, it looks like a resistor of about 90 ohms, with the red line showing what that resistor would do in a simple voltage divider. Here's another current source that I actually used once upon a time to dim a string of high-power LEDs. I chose to run the LEDs from an unregulated power supply so that the voltage regulator didn't have to handle all the LED current. If I remember right, it was about 300 milliamps. I used a bigger power transistor, not the wimpy little transistor I'm showing here. I drove the base with a pulse width modulated output from a microcontroller. On the breadboard, I'm using a little PWM circuit built from a 555 timer. I'll put the schematic on the project GitHub and link in the video description. The schematic shows a log taper pot for the pulse width adjustment, because the human eye's response to light is nearly logarithmic, and a log taper gives us a usable range of perceived brightness. The diodes will bring the logic high voltage down to about 3 diode drops above ground, about 1.8 volts. Logic low will have the base less than a diode drop above ground. That breaks the rule that the transistor keeps the emitter 1 diode drop below the base. The transistor can't pull it below ground. It's a valve, not a pump. It goes into a state called cutoff. When a transistor is cut off, the collector to emitter current path looks like an open circuit, which is just what we want when the LEDs aren't supposed to be on. For the logic high voltage, the emitter voltage will be 1 diode drop down, or about 1.2 volts. We've sized the emitter resistor so that the emitter current is 18 milliamps or so, 10% below the rated current of our LEDs. That current will flow at the collector. We don't need a current limiting resistor on the LEDs because we're limiting the current with the transistor. Let's try this one out on the breadboard. We'll turn it on, and even with these little 20 milliamp LEDs, the LED brightness goes from a dim glow to a brightness that hurts my eyes if I look at it directly. So there's our first practical transistor circuit, a logic-controlled current source. You might wonder why I chose pulse width modulation. For one thing, it's easier to get a PWM signal from a microcontroller than it is to get an analog one. For another, it gives more efficiency because the light curve of an LED isn't linear. LEDs are considerably more efficient close to their rated current than they are with only a trickle of current. This has been a long video. What have we learned today? We can think of a transistor as a valve that adjusts the flow of current between collector and emitter. We've learned that we can often think of it as adjusting the current in such a way as to keep the voltage on the emitter 1 diode drop below the voltage on the base. We've seen 2 other operating regions. Saturation, where the collector resistance is high enough that maximum conduction on the transistor won't bring the emitter voltage low enough. And cutoff, where the base voltage is low enough that turning the collector to emitter path off completely still won't bring the emitter up to a diode drop below the base. The collector to emitter path of our transistor looks like a current source only in the active region. In saturation, it looks like a small resistor, about 90 ohms in the circuit we tested. In cutoff, it looks like an open circuit. And we've designed a useful LED dimmer circuit using only this idea of a constant base emitter voltage and Ohm's and Kirchhoff's laws. Next time I'll continue with current sources and show how to convert a current source into a voltage amplifier. In the meantime, stay tuned, stay safe, stay healthy, stay curious, and take care of one another. Bye!